All right, let's dive into a really wild idea, something that could completely flip our understanding of the universe on its head. It's called Theory 6, and the core of it is this. What if reality isn't actually made of particles? What if it's all just one continuous field that only looks like particles when we're looking at it?
I mean, think about it. We see particles everywhere, right? In colliders, when we look at atoms, the photons hitting your camera sensor, they seem so real, so fundamental. But what if they're not? What if every single particle you've ever heard of, electrons, photons, the whole gang, is just a temporary illusion? Just a little blip, a little flicker in something way, way bigger.
So, you might be asking, why even question a theory that's been so unbelievably successful? I mean, quantum mechanics works. The thing is, it's just, it's weird. Under the hood, it's built on some really strange mathematical tricks. It uses things like anti-commuting variables for matter, which honestly, nobody really knows what they are in the physical world. It kind of feels like a patchwork quilt. It keeps us warm, it gets the job done, but when you look closely, you can see the seams. And some physicists think there might be a better, cleaner way to describe reality.
Okay, so here's our game plan. We're going to start by really digging into quantum theory's big problem. Then we'll introduce this amazing analogy of the universe as an image. After that, we'll see how these fields can collapse to create particles and how that simple idea just might solve some of quantum's biggest puzzles. And finally, we'll get to the grand ambition, how this whole thing could lead to a theory of everything that starts from almost nothing.
All right, first section. Let's talk about quantum theory's big problem. Why are physicists even looking for a new explanation in the first place?
So here's the deal. Standard quantum field theory, as powerful as it is, has some, let's call them mathematical quirks. Instead of dealing with real physical values, it uses these abstract things called operators. And for matter, for electrons and stuff, it leans on these super weird anti-commuting variables that don't really map onto anything you can actually go out and measure. It's like the theory gives us the right answers, it makes incredible predictions, but it doesn't give us a clear, consistent picture of what a particle really is. It's a collection of tools that work, not necessarily a coherent story. Okay, section 2. This is where Theory 6 comes in and offers a totally fresh start. It suggests we can understand the universe using an analogy that's actually super familiar to all of us. The big idea here is something called field collapse. And right off the bat, let's be clear. This is not the same as the wave function collapse you might have heard about in quantum mechanics. It's different. The idea is that underneath it all, reality is this perfectly smooth, continuous field. And the particles we see, they're just what happens when that field suddenly gets crunched down or localized into discrete, little pixelated values. It's almost exactly like taking a beautiful, high-resolution photo and compressing it into a JPEG. So let's really lean into this JPEG analogy, because it's perfect. Imagine you start with a continuous, flawless image. That's our fundamental field. The next step in compression is to break that image down into all the different frequencies that make it up. Then, and this is the key part, the process rounds off the values for those frequencies. It makes them discrete. And what you're left with is a compressed file made of distinct pixels. And in this theory, those pixels are the particles. All right, on to section 3. So how do these fields actually collapse? How does this rounding off, this discretizing, actually happen? What are the rules of the game? Well, this is where it gets really elegant. The theory says there are just two incredibly simple rules, and those two rules are enough to create the two basic kinds of particles in the entire universe. And here are the rules. It's shockingly simple. For bosons, those are the force-carrying particles like photons, the field's amplitudes can only collapse into values that are the square root of a whole number. So square root of 0, of 1, of 2, and so on. But for fermions, the stuff that makes up matter, like electrons, the rule is even simpler. Their amplitudes can only be 0 or 1. That's it. It's a binary switch, on or off, nothing in between. And this simple on or off rule for fermions, it has this really cool connection to technology you hear about all the time. Quantum computing. The basic unit of a quantum computer is a qubit, right? It's basically a system that can be a 0 or a 1. And this theory says, hey, that's not some spooky quantum thing. That's just a direct result of the fundamental rule that governs all matter in the universe. Qubits are just tapping into this basic anti-commutation relation. So what's the payoff for this super simple binary rule? Oh, it's a big one. It naturally explains one of the most fundamental rules of physics, the Pauli exclusion principle. You know, the reason you can't have two electrons in the exact same state at the same time? According to this theory, it's dead simple. Their field amplitudes can only be a 0 or a 1. You can't stack two ones on top of each other, because the result wouldn't be a 1. The rule forbids it. The exclusion principle just falls right out of the math. No extra weirdness needed.
Okay, section 4. Now for the real test, any new theory has to be able to solve the old puzzles, right? So let's see how this idea of a classical collapsing field handles one of the spookiest, most famous experiments in all of physics.
The double-slit experiment, the classic quantum head-scratcher. You fire one single particle, say an electron, at a barrier with two slits in it, and somehow that one particle acts like a wave and seems to go through both slits at once to create an interference pattern on the other side. How is that possible? This is pretty much the definition of quantum spookiness. Well, Theory 6 has a really elegant answer, and there's no spookiness involved. Here's how it works. When you're not looking, the underlying continuous field flows through both slits, just like a wave in water, and naturally creates that interference pattern. Simple. But the moment you try to observe which slit it goes through, that very active measurement forces the field to collapse. It snaps into a single discrete particle before it gets to the slits. And that one particle, of course, can only go through one slit. The interference pattern vanishes. See? Both results explained by the exact same mechanism. It's all about when the collapse happens. And look, this isn't just some nice story that happens to fit. This is the really crucial part. The mathematical equations that describe this classical field are identical to the Schrödinger equation, which is the absolute bedrock of quantum mechanics. So this new theory gets all the same results, all the same correct predictions as the old one. The difference is that it does it with a much simpler, more intuitive picture of what's actually going on. It gives us the right answers without all the spookiness. All right, final section. We've seen how this theory can handle quantum weirdness on the small scale. But its ambition is, well, it's way bigger than that. The ultimate goal here is to take this simple idea of a collapsing field and build a complete theory of everything. And it's not just a vague goal. There's a 4-step plan. Step 1, you take the entire standard model physics and reimagine it as a classical field theory. Step 2, you apply those simple JPEG compression rules we talked about to make it discrete. Step 3, you give each of those little discrete bits, those quanta, a specific path to follow. And then, step 4, the truly mind-blowing part, you connect all of this to the fabric of space-time itself. And when you do that, the theory makes a staggering prediction. Every particle we see is actually a tiny rotating black hole. It's exactly like the source material says, from nothing emerges everything. I mean, the claim here is absolutely incredible. It suggests that if you start only with the basic symmetries of space-time, just the fundamental rules of geometry and time, you can derive everything else, the whole zoo of particles, all the forces of nature, the entire universe, all without needing any of that spooky quantum stuff at the start. So what we're left with is a picture of the universe that's, well, it's classical. It's deterministic. It's all governed by a set of simple, unbreakable rules. The randomness and weirdness of quantum mechanics, in this view, is just an illusion. It's what happens when our measurements force a smooth, continuous reality to snap into a pixelated, discrete one. And that leaves us with one heck of a final question to chew on. If we, and everything around us, are just the result of these rules playing out, then what are those rules that the universe always, always obeys, right down to the letter?